So let's suppose that we are faced with one of these linear non-homogeneous differential equations. So here you can have this function of t f. So it should say f of t really, but I don't want to write that every time. So just remember f is a function of t. We're faced with this, and suppose that we have already solved the homogeneous differential equation. So for my schematic back here, we already got this part. We already got x homogeneous general. So we got this. We're still trying to get this. All right, well, if we have already solved this, meaning we got the general solution, that means we got two linearly independent solutions, right? So let's say x1 and x2. So they're like x1 of t, x2 of t, but I don't want to write that every time. Let's say x1 and x2 are two linearly independent. And I'm making it 2 just to make it easier to write things, but you could do this for n by n systems. And I would say suppose here we've got n linearly independent solutions. Suppose these are two linearly independent solutions to x prime equals ax. So what does that mean to say they're solutions? To say they're solutions means if you take, so to say x1 is a solution means if you take the derivative of x1, well, that's the same as applying the matrix A to x1, right? And to say x2 is a solution is to say if you take the derivative of x2, then that's the same as applying the matrix A to x2. There's actually a way of mushing both of these equations together into one matrix equation. So do it like this. So notice that each of these equations is an equality between two column vectors, right? This is a column vector, like a 2x1 object, and this is a column vector, and when you apply this 2x2 matrix, then this is also a column vector, the output. So these are equalities between column vectors. So I can write it like this. Here I can write x1 prime as the first column, so this is like vertically 2 entries, and x2 prime as the second column. So that's this here, and this here is the second column. And then put this one there, and this one there. So this is the first column, and the right-hand side here is the second column. So hopefully you agree that this equality between these two matrices is the same thing as these two equalities between these two column vectors. Well, check this out. This matrix, which has as its columns A applied to individual things, this can be written as the matrix multiplication A with this matrix, whose columns are x1 and x2. That's how matrix multiplication works. And so look at this. We have A applied to this matrix equals, and then what's on the other side? The same matrix, but with derivatives on everything. Remember, when I put a derivative on a column vector, I'm really just putting it on the individual components, right? So this is a 2x2. It has 4 entries, and there's a derivative on each of those 4 entries. And here's the same 2x2 matrix without the derivatives. That is interesting. So that is a nice, small, compact way to state these two equations. To state that x1 and x2 are individually solutions. So this matrix is pretty useful in the context of this particular differential equation that we are looking at. This is called the fundamental matrix, and I only know that because I saw it in the textbook. I've never actually used that term myself before, but apparently it's called the fundamental matrix. But clearly it is a pretty fundamental matrix, at least it's important, right? So let's call it phi. So this is a function of time, notice, because these are functions of time. So this is a matrix whose entries are all functions of time. So if n is 2, if we're looking at 2x2 systems, then phi of t, our fundamental matrix, consists of 4 entries, which are functions of time. And what we're observing here is that phi prime of t which is take the derivative of all 4 entries, so that's the left-hand side here, equals a phi of t. And I'm going to drop the of t just to make it look easier to write. So phi prime is a phi, and just remember that phi depends on time. Okay, that's pretty good so far. All I've done, though, is communicate in a sort of efficient way, notationally efficient way, communicate that x1 and x2 are solutions to the differential equation. That's all I'm doing so far. Now, how about, can I use this to write the general solution? So what's the general solution to the homogeneous differential equation? So general solution to x prime equals ax is c1 x1, right? If I have my 2 linearly independent solutions, the general solution is c1 x1 plus c2 x2, where these coefficients, c1 and c2, can be any real numbers. So they can just vary. You've got these 2 free parameters that can take on any values, and depending on what you choose, that's the particular solution you're looking at. So this is a 2-parameter family of solutions. That's your general solution. So you could call this x, what were we calling it before? X homogeneous general. X homogeneous general. And indeed, there is a more efficient way to write this using phi, the fundamental matrix. Okay, I kind of wish I put this on the other side. Let me do this. Here is the more efficient way to write it. So what are we doing here? We're taking a linear combination of these 2 vectors. They're actually vector-valued functions. They're time-dependent. They have t's in them. But let me just call them vectors. So we're taking a linear combination of these 2 vectors. And the coefficients are c1 and c2. How would you write that using matrix language? If you have a matrix whose columns are these 2 vectors, here's how you would write it. Like that, right? It's just this matrix, whose columns are these, being applied to this vector. That's how you form this linear combination. So look at this nice compact way to write the general solution to the homogeneous differential equation. You just take your phi, which is a matrix whose columns are your 2 linearly independent solutions, and you apply it to an arbitrary vector. So what we were thinking of previously as 2 free parameters that are being used to describe the 2-parameter family of solutions, we can now view it as 1 free vector parameter. So you could view it like this. Phi, the matrix phi, applied to a free vector, C. And again, the beauty of this is that if there were more than 2, if the system from the very beginning were like an n by n system, say 3 by 3, and you have 3 unknown functions x, y, z, then the same notation here, equally efficient of notation, can be used here to express these ideas. All right. So to summarize, starting with a homogeneous differential equation like this one, if you solve it and you get 2 linearly independent solutions, then you can stuff them into a matrix. Call that phi. That's called the fundamental matrix. Then you can use that matrix to communicate certain things very efficiently. One, you can communicate that these are solutions, x1 and x2, by just writing this. This is all you would need to test to make sure that you really do have solutions. And secondly, you can express what is the general solution by just writing phi applied to a vector of constants c. But that's all dealing with the homogeneous. So how do we deal with the non-homogeneous? Well, think back to how variation of parameters worked. Back in chapter 2, do you remember why it was called variation of parameters? It's because the way we derived the method was by starting with a general solution to the homogeneous differential equation, where you've got these parameters that are constants, and then we varied those parameters. We said, what if we let these vary in time? What if we let c1 and c2 be actually functions of time? Then we probably wouldn't expect to get solutions to the homogeneous differential equation, but I wonder if choosing certain functions of time for these coefficients here would lead to a solution to the non-homogeneous differential equation. And then we went from there, and that's how we derived variation of parameters. So it's because we varied these parameters. Here, we've actually vastly simplified things because we're viewing the parameters as one vector parameter. So we only need to vary this one vector parameter. So here's our guess for variation of parameters. Perhaps, let's leave it kind of open as to whether this will work or not, but it will work in the end. Perhaps a solution, perhaps a function of the form our original thing, but with these being allowed to be functions of time. So let me say, so let me just emphasize that phi is a function of time. It always has been. But now I'm going to allow this vector of coefficients to also possibly depend on time. Perhaps a function of this form can be a solution to the non-homogeneous differential equation x prime equals ax plus f. And remember here, f can depend on time. So there's the varying of parameters. So this is our guess. So let's plug in our guess. So we're guessing x equals this. X of t equals this vector valued function of time. And keep in mind the types of the different things here. This is a matrix valued function of time. So if you're looking at the 2 by 2 situation like we seem to be here, then this is a 2 by 2 matrix. It has 4 functions of time in it, and then it's being applied to this vector of now functions of time rather than a vector of constants. And they're unknown. I'm asking, is there a possible pair of functions, c1 of t and c2 of t, such that when I package them together into this vector, c of t, then x equals this is a solution to the non-homogeneous differential equation. And just to remind you where we are, the point of this is to get this red part, find one solution to the non-homogeneous, so that we can then get the ultimate thing at the end. So let's plug this in. So plug in the guess into the differential equation. All right, so this is our guess, x equals this. So first we need to know what is x prime. Right? Remember, the differential equation is this. So I need to plug in this x, so this will go here, but its derivative will go here, right? So I need to know the derivative. So need x prime. X prime is, so what happens when you take the derivative of this? It turns out that it works really nicely. You can do the product rule. So let me not write the of t here, but remember that c is now a function of time. I guess that's obvious now because I'm writing c prime. So the product rule actually works when you've got a matrix of functions being applied to a vector of functions. So that is awesome. That does a lot of computation for us that otherwise we would have to just write things out in terms of individual components. It would just be a mess. So that's just really awesome. Now let's do the substitution. So the left-hand side, so just to emphasize that what I'm writing down is this here. So the left-hand side is phi prime c plus phi c prime, right? That's x prime is this. And then the right-hand side is x is this, so phi c plus f. Okay, so there's the left-hand side, that's x prime. There's the right-hand side, that's ax plus f. I'm just putting in x equals this. Okay, but remember that phi isn't just any old random matrix of functions. It's built out of x1 and x2, which were solutions to the homogeneous differential equation. And we express that fact by saying phi prime is a phi. Phi prime is a phi. So this is the fact that phi was built out of solutions to the homogeneous. Phi prime is a phi. So the phi prime you see here is actually a phi. So let me rewrite this, but with a phi instead of phi prime. And look at that. I don't know if you remember how much more complicated it was to get nice cancellations and even use a fact like the fact that we were starting with homogeneous solutions back when we were doing variation of parameters in chapter 2. It was way more complicated. But this is just great. So we end up with this very tiny looking little system of equations. And remember, the goal is to find C of t, right? That's the goal. We're trying to find a pair of functions, C of t, such that this is a solution. So this is a way of finding C prime. How would you find C prime from here? You would have to solve for it, right? So you need to apply the inverse of this matrix. Okay, matrices are not always invertible, but this one will be. That's because you built it out of two linearly independent columns, right? These had to be linearly independent solutions. x1 and x2 have to be linearly independent. So phi will be definitely an invertible matrix. So look at that. We got C prime. Then how do you get C? So these, in the context of any problem setup that you're starting with, here you have C prime in terms of things that you're given, right? Like f of t, you're given. Like at the very beginning, you're faced with this. F of t is the right-hand side of your non-homogeneous differential equation. And then phi, well, phi is not exactly given to you at the start, but phi is what you get when you solve this. It's just this matrix of with the columns being x1 and x2. So this is all functions of time that we have. So right now we know C prime as a function of time. Or rather, we know C1 prime and C2 prime as functions of time. They are the two components of this vector here. By the way, f is a vector. I stopped writing the vector symbol, but it's been a vector this whole time. All right. So how do you get C then? Integrate, right? So one way to look at it is here you've got sort of, yeah, probably, I think you'll appreciate this more if we do it, if we split it up a little bit first. So this is like C1 prime of t, C2 prime of t. That's the left-hand side here. That's C prime, right? And then on the right-hand side, we have two functions. Some complicated thing, which is the first entry of this, and some other complicated thing, which is the second entry. So let's call this complicated thing number 1 and complicated thing number 2. Then what's C1 of t and what's C2 of t? C1 of t would be integral of complicated thing number 1 with respect to t. C2 of t is the integral of complicated thing number 2 with respect to t. Is there a shorter, more compact way of expressing that fact? Yes. Because if you write integral and then a vector of functions like this, so that's just the meaning of, that's just what we take it to mean when you write integral of vector valued function like this. I don't know if you've seen this before, maybe not. Probably you've seen it if you've done Math 6a, but now you're seeing it. Integral of a vector valued thing with respect to t just means, basically, it means this. You see? So just like we do with derivatives, right? Like if I write like these primes here, I can put the prime symbol on the outside like that. You can think of that as being how we define derivatives of vector valued functions. It's actually not how we define it. The derivatives are defined for vector valued functions are defined in a different way using limits. It's pretty cool actually, but then you can prove that it's the same, and so it's something one proves at some point, that the prime can be pushed inside. But this is not a class about proofs. Okay, so what that justifies is the following. C of t is this integral. Okay, and now I'm going to write an integration variable, so I had better be very clear about what depends on time instead of being lazy like I have been. Let me be very clear about it. C of t we're talking about here is the integral dt of the following vector valued function of time. Phi depends on time, right? So the inverse of phi as a matrix depends on time. Actually, the inverse symbol was in a terrible spot there. It's the matrix phi of t, and then take the inverse of that matrix. That's really what I should say. And then apply that matrix that you get when you do that to f, which by the way is also a function of t. Okay, so there's our C of t. There's our C of t. And if C of t is defined in this way, then its derivative will be the correct thing, and that will make x, which came from our guess here, that will make this x here be a solution to the differential equation, to the non-homogeneous differential equation. And if you want, so let me just write down that we now have successfully found, so x equals, okay, let me go back and look at what the guess looked like, phi c, so phi x of t equals phi c, but instead of c, let me write this. Oop, what have I done? Okay, I think we're back. So instead of writing c here, so x equals phi c, but instead of writing c, let me write this full thing here. So this function here is a solution to x prime equals ax plus f. All right, awesome. So that's how you do this red part. So let's write the final answer. Let's write the final thing at the end. Now we only wanted one solution, right? But I've written this in terms of a definite integral. In terms of an indefinite integral, which means that this integral will have sort of a plus c inside it. Not this c, but a plus something else, plus k. I actually just need one solution, right? Here it says find one solution. That's all I need. So in order to just pick one of the many solutions in the family that I'm describing here, it's a family because the integral has a plus k in it, let me make this a definite integral. So how about I make it an integral from 0 to t, but definitely I should not confuse the t that I'm integrating out to with the integration variable, so I really don't want to confuse those. So let me replace these t's with just some other variable, s. So s is the dummy variable of integration. And the t dependence showing up here is in the limit of the integral. And I didn't have to put 0 down here. You can pick any constant down here and it'll work. Picking different constants is the same as basically that plus c or plus k, that freedom that you have when you write an indefinite integral. So we're just kind of picking one. I think 0 is a good one to pick if your initial conditions are based at time 0, because then when you plug in t equals 0, this will just vanish, and that will be convenient, as you will see. All right, so so I'm calling this x, but let's give it a better name. in terms of the larger context that we're in. We're in this context where we've already got x homogeneous general, and we're trying to find x non-homogeneous particular. That's what we just found. This is non-homogeneous particular. That is what we found. So then what's the general solution? So this is just one solution to this. The general solution to this, x prime equals ax plus f, is, here goes, x of t, general, whatever subscripts you want to put, x of t equals, and then I need to put the homogeneous general solution. We described that before as phi of t applied to, let's see, what notation did I use before? X homogeneous general is phi of t applied to c. That's unfortunate that I had used c for that also. I should use a different notation since I just don't want to confuse it with the thing that I'm calling c of t here from my variation of parameters. So how about I call this one k, since that's what they call it in the textbook. So k, and I'm not just being lazy and not writing of t. This literally is a constant. It's not laziness here. Plus this thing that we got. So that was, I think that was a lot more simple and painless than what we did in Chapter 2 with variation of parameters. There was no random side conditions coming out of nowhere, and we ended up with a very nice, basically, formula for whenever you can handle the green part. Whenever you can handle the green part, we have a formula that gets you this red part. So you can always solve non-homogeneous differential equations. Of course, this can be horrible. So it looks prettier than the variation of parameters we had back in Chapter 2, but remember that this inverse, which I've written in an incorrect way again, when I broke that notation, I rewrote it, and I rewrote it incorrectly. Sorry about that. This inverse is the inverse of a matrix valued function, right? So like this is a function, this is a matrix, and then we're taking its inverse. So that's already kind of a gross thing, right? If the original functions inside phi were nice, then when you take this inverse, you're going to probably get something not very nice. And then you're applying that to this function. This could be a terrible, terrible integral. So we don't know. Usually this integral will be just horrible and you will not be able to do it. But at least written like this, it looks pretty, right? All right, so let's do an example in the next video. And I'll just give you probably one homework problem where you get to play with this.